This is it? Okay. Good afternoon for those who stay this afternoon, and good morning for those who are just here now. Very happy to be here now and to talk about not on Mars. All people knowing me know that I long advocated for the Mars mission, and the Mars mission do not need to be advocated. You have seen that ExoMars is, I hope, on track. MSR also. We do a lot of things for MSRs, in particular with the US, ESA, also with China, I would say. So the Mars program is sort of already clear. What I would like to emphasize here is to propose really a new mission. It's not new in the minds of many people because we know that that has to be done in a sense as soon as possible. But I would like to once again elaborate a little bit on the reason why return sample from a comet would be really the things to do and the things to go, the direction to go in the coming decades. Again, the earlier the best. So for those who want to contact me, because I know that most of the questions go afterwards, do not hesitate to email me, and I like this sort of interaction that we have here. So, of course, the basic reason why we've got to go to the comet to get the water is just because the water that we have on the Earth comes from comets. There has been a lot of elaboration whether or not the oceans are really made from comets. I'm not going to be long on that because I have no time, but obviously when it was cold in very early time, the only possibility to get water was to go from the outer solar system. And here you have an idea that the inner planets come from the center part of the solar system, very probably, and that's the reason why the mass of Mars is so small, actually. And the only possibility to get water, because the center was not hydrated minerals, is to get the water from the ice outside. So very early on, there has been a lot of turbulence in the disk, and most of the grains with ice come from outside and were injected towards and of course at the same time softened material went outside. And that's why I make this sort of graph here to show that during the accretion themselves of all the inner planets, you have a lot of impacts from outside that produce the water inside there. Of course, one of the questions was how you get from this to this. You've got to have the water that goes to the surface. It's not my talk here, although it's very interesting in itself, and that would deserve an entire talk on that. The idea that I have is that after the accretion, with all the water in the bulk, you have to have an impact to explain not only the formation of the moon, but many other things, including the possibility that when the magma just cooled down, the water went to the surface, a fraction of it in the ocean that Enrico told about. Another fraction, probably even higher, is in the mantle, was in the mantle. That's why we have plate tectonics here. And just to once again explain that this impact that makes the moon was very important for a lot of reasons. Most of the evolution of the Earth really depends on the parameters of this impact. And the reason why we have 10 big plates here and only one on Mars and maybe thousands on Venus is directly connected to that possibility for the water to go to the surface. Anyway, the water comes from that, and that comes essentially from the comet themselves. It happened that the comet has played, and that's what I will focus on now, very importantly here. And the reason why we've got to see a comet better than we did now is not only because water is H2O. H2O in itself, really, it's not, you don't need to go to a comet to discover that. It's because the water is embedded in many other things. And as I said the other evening during the debate, the evolution that we have here have to have some water, but not only water as plain water. If you have distilled water, it's not habitable by itself. It's all what you have inside there. And the question is, what was inside the water in the comet themselves? And for that, you got to be there and receive that. So it happened that Rosetta and Philae, in which we were involved also a lot, has, to me at least, modified dramatically the idea that we have a comet and the role that comet may have played. And in particular, the comets really have modified the evolution of the planets in which bodies similar to the comet that we saw have been involved there. In particular, because what I call the pre-planet history of the inner planets is really directly connected to what happened and it been still frozen and recorded in the comets here. Before we went there, you know that comets were considered as dirty ice. In other words, for everyone, a comet is so hugely embedded with ice that when it comes to the sun, it makes these big tails and everything. So that's what the idea. And actually with Rosetta, we discovered that it's not the case. That ice in a comet is only very limited in volume and in importance, maybe 10, 15, maybe 20%, no more than that. But most of that is organics. And organics, I will show a few pictures here, but ice and organics are intimately mixed in. And that's why I created, if I can say so, the word. If in organics you put an E, it's organize, and that's really what happened. Ice is really embedded in the organics, so comets should be called organize, actually. And what you see in this picture that we took with Philae when we landed a few tenths of centimeters ahead of us, do I have the, yes, all this material, you have to stress the images to see something. It's really black. Essentially, all this is, with your eyes, you will just see something like that, only black things. When you stretch the scales, you can sort of see things, but the albedo here is only 2 to 3%, no more than that. It's very absorbing. All these are grains, organic grains. And when I say grains, it's really millimeter scale grains. It's huge structure made of organics, but you also have a few points like this one and many others, which are the ices which are still there. So you have a mixture of ice and organics in a comet, and that's the beauty of that. So yes, inside you have plenty of organizers, and you have on the top of that, what I put here, a small crust, which is a synthesis crust, and that explains why Philae actually rebounds several times, because by compression, essentially, it looks like a trampoline. So it's important in particular because these crusts simulate or mimic what happened when such a body entered the atmosphere of the Earth very early on with a dense atmosphere. It may have protected the interior of the content of the nucleus that could be finally embedded in the oceans, in the planetary oceans. So it's been, you could preserve the material from the comet entering through the atmosphere through the sintering of this crust. So the planetary oceans, again, as I explained already during this conference several times, is not plain water. It's water plus a lot of things there. And what is in there is really the evolution of the Earth that translated that in terms of catalyzers, different ingredients that were present there. And it is a combination of these and the organic themselves, which are the key ingredients out of which finally we could have the evolution towards life. So that's what we said, that getting a comet here gives clues to that. So of course the H2O ice will tell us in particular with the D over H ratio what is the condition in which the H2O formed. You know that D over H is very sensitive to temperature, but it's a few kelvins or a few tenths of kelvins, you will have a different D over H, and that will tell you essentially what was the fraction of these comets when you get one that would have contributed to the ocean here, water ocean, but more importantly, all what I call the impurities within the ice is fundamental, and no one for the moment has even thought of that. But for the organics, exactly the same. The organics are not the trivial organic that you can think of. Of course, out of carbon, CO, CO2, all these is made, but you can also make a lot of other things. And during the pre-solar evolution of our cloud, the organics have been modified, and that's really the key things now to understand to which level the evolution of the organics here can have played a role in the further evolution of the organic chemistry when these grains went into the oceans that themselves were evolved by contingencies. So what are the specificities? Very likely the early sun even modified the chirality of such of them, and we could have also already some excess of chirality that drove the fact that, as you know now on life, essentially all the amino acids are left when the sugar are right in chirality, and that's probably already done with the early evolution of these organic grains. Unfortunately, on Philae, we didn't have time to measure that, although we have an instrument that could have done that. So we've got to do that with a return sample now. So the coupling of the H2O ice and the organics is fundamental to understand really the evolution of the carbon-rich chemistry towards life on Earth. So this is what I summarize here. Within the H2O ice, not only the D over H, but what are the radical, the ions, everything which can be mixed in already there, and to which extent these impurities, quote mark, have been able to interact with the organics themselves to modify the organics at a point that these organics, modified by the interaction that had during the their pre-solar history, had played a role when they entered the planetary ocean that were also mixed with catalyzer like iron, whatever they could have there. So this is what we would like to have, and that's why I essentially summarize here. Both the ice and the organics have specificities, very likely so. It's not only H2O, it's not only regular organics, it's very specific organics and water that we have in the nuclei of any comet. If we have that, we'll be able to characterize what were the inputs in the planetary ocean, the terrestrial ocean essentially, that could drive the evolution towards what we are here now. So that's what I'm saying here, maybe a little too low. Returning cometary sample really absolutely essential if we want to understand what has paved the evolution of organic chemistry towards life here. What we do on Mars, what we'll do on the, we'll see with JUICE in particular in the oceans, which are deep oceans, is important also because that will tell us other way for the same organic chemistry to have evolved towards something different that we will discover, both on Mars and there. And out of that, we might, by extrapolation, understand what happened on Earth to drive the organic chemistry towards what we have now defining as life. So it's not true that there has never been such return samples. We have the Stardust mission. We did that 20 years ago almost with the Will 2 things. But essentially they went in the coma, which is not necessarily representative of the entire nuclei, but essentially the collection was at so high velocity that the carbon chemistry essentially has not been preserved. So it's very difficult to extract from the Stardust the information of what carbon chemistry was there. The really two present missions which give us some clues on what to do there is the first one is the Hayabusa 2 Japanese missions, went to a carbon-rich asteroid, Ryugu actually, and Ryugu, sorry, cometary water. And Ryugu has been selected, collected, and brought back to the 2 years ago already to institutions which are in the Aizas, close to Tokyo in Japan. And we are now, grain per grain, analyzing there to have the idea that some of the grains have preserved the carbon chemistry really primordial, not evolved at all, not modified by any terrestrial environment or whatever it is, and it's probably, but very difficult to work on that, there is very few grains, it's probably the very first, I would say, cometary return sample from the organics themselves, not for the water, but for the organic themselves. And now NASA has a similar mission named OSIRIS-REx, which is still on its way to the Earth. We'll arrive September 24 this year, and so in a year from now, we'll have 2 sets of samples for carbon-rich asteroids to work with. And they can sort of prepare what we could be doing, or what we will be doing when we have cometary samples back to here. So with that said, I consider really that the next critical step in the quest for the evolution of the organic chemistry towards life will be these missions of a cometary return sample. Thank you.